Our next topic is organic chemistry. So what is organic chemistry? Now, in the very first definition of organic chemistry was the study of compounds that are made from, that are of plant or animal origin. That was the very first definition of organic chemistry. However, with time, it was discovered that it is possible to obtain those same compounds by synthetic means. For instance, urea is found in urine, yet urea can be synthesized in the lab. So if we define organic substances that are of organic origin, yet urea is being made from the lab, does it then mean that it is both organic and not organic? So in order to deal with that scenario, then another definition was crafted. So what is common with all the organic substances is that all of them will have carbon. So they may either be synthetic or man-made, but they all have carbon. So carbon is a common denominator of all the organic substances. So we now therefore define organic chemistry as the study of the compounds of carbon. However, we have already studied oxides and carbon. So oxides and carbonates are studied in inorganic chemistry rather than organic chemistry. So our working definition shall therefore be: organic chemistry is a study of the compounds of carbon apart from the oxide and the carbonate. Now it is imperative to note at this point that carbon will form very many compounds. That is what justifies the study of organic substance as a separate chapter as such. So because carbon will form very many organic compounds. Now I wish to remind us that carbon will always form covalent bonds. It is one of the substances with the highest tendency to form covalent bond, because it is going to be very difficult to remove 4 electrons. So very difficult to add 4 electrons. So in all its compounds, carbon will form a covalent bond. Even when you look at the carbonates, for instance, we are talking about sodium carbonate. Yeah, the sodium carbonate may be ionic, but in the carbonate, carbon has formed a covalent bond. So it will rarely, if ever, form an ionic bond, because you need to remove very many electrons. Removing 4 and adding 4 will both require a lot of energy, and that will rarely occur. Now, why does carbon form very many compounds? Now, there are 3 reasons why that is so. Reason number 1, the unique ability of carbon to catenate. What is catenation? Now, catenation is a bonding to cell, the ability to bond to cells. So carbon will bond to another, to another, to another, and in the process you are going to get a very long chain. And I think this can be attributed to the strong carbon to carbon bond. The fact that carbon is a small atom. Is a small atom, therefore the pull of the nucleus to these electrons that are being used in the formation of the covalent bond will be very strong. So how does this explain why carbon forms very many compounds? Right, so you can have a compound of carbon with only 1 carbon atom, and it's going to be different from one that has 2 carbon atoms. And you see, there is an infinite number of carbon atoms, so you can have very many of those compounds, as many as the number of carbon atoms that can join to each other. And you have said that there are very many, can join to form very long chains. Furthermore, these chains can also cross up to form rings. They can cross up to form rings. So in what we call cyclic compounds, as opposed to aliphatic compounds where we have straight chains. So cyclic compounds, we even have some chains where we have benzene rings that we call the aromatic compounds. The other reason why carbon can form very many compounds is due to the fact that it can form multiple bonds with itself. So you can have compounds with carbon to carbon double bonds, compound with carbon to carbon carbon triple bond, something like that. So if you had very many compounds with carbon to carbon single bonds, then you can multiply. You can have the same number, this time with carbon to carbon double bonds. So you'll have twice as many compounds that you initially had. Then you also get some other compounds with triple bonds. So the infinite number of compounds have now been multiplied by 3. So infinite times 3 now is 3 infinity. I don't know how much that is. Now the other reason there again why carbon can form very many compounds is its ability to bond with other elements. It has a unique ability to bond with other elements, form strong covalent bonds with other elements like hydrogen, nitrogen in nylon, proteins, yes, with oxygen, can form a bond with oxygen in alkanols, alkanoic acid, and such compounds, halogens in like what we refer to as the CFCs. So you have so many. It can also bond. So now that you have very many compounds with maybe carbon to carbon single bond, then you multiply by the ones that are formed with carbon to carbon double bond. You multiply now with compound that contains carbon and nitrogen, carbon and oxygen, and you have a scenario where the carbon is forming an infinite number of compounds. And now we will start by the study of the compounds in which carbon is bonded to hydrogen. That is the first thing that we shall be concerned with. When carbon bonds with hydrogen only, such compounds are referred to as a hydrocarbon. So what is a hydrocarbon? A hydrocarbon is strictly a compound that is made from carbon and hydrogen only. Carbon and hydrogen. Actually, all organic compounds are going to have carbon and hydrogen. That is granted. Now, but if it has carbon and hydrogen only, then it becomes a hydrocarbon. So if you're asked to define a hydrocarbon, remember to include the word only, because if it has carbon, hydrogen, something else, then it is not a hydrocarbon, yet it contains carbon and hydrogen. So hydrocarbons actually can be classified into 3. And the classifications are, as we shall discover, are called homologous series. So we will have hydrocarbons that we will call alkanes. What are alkanes? There will be hydrocarbons that have a carbon-to-carbon single bond. Single bond, the ones we started with there. Now, when the hydrocarbon has a carbon-to-carbon double bond, at least one, not necessarily all of them being double bond, then it's going to be called an alkene. Then actually we have others that will be called alkynes that will have a carbon-to-carbon triple bond. So all these are hydrocarbons, but they are 3 series depending on the bond between the carbon atoms. Now we start our study on the alkanes, and we have just mentioned that alkanes are hydrocarbons, meaning they are compounds of carbon and hydrogen only, but they will have a carbon-to-carbon single bond. And now that excludes the very first one, because as we can see, this one doesn't have a carbon-to-carbon single bond, yet it is the very first of the alkanes. I have tried to illustrate the bonding in carbon. Now, so when it bonds with hydrogen, it's not stable yet, because it has 1, 2, 3, 4, 5. So it will need another one. Those are 6. And then it will need another one, and yet another one. So that is a bonding in the simplest of the alkanes. Note that the carbon must form 4 bonds because it requires 4 more electrons to be stable. So we represent that. That's the dot and cross diagram that we drew in form 2. Now we can summarize that structure like I've shown there. The carbon bonded to 4 hydrogens, and then we can also summarize it into 1 carbon and 4 hydrogen. Now we can repeat that for the next structure with 2 carbon atoms. So we said the first thing that will happen is that the carbon will bond to another carbon. Now, and as we have seen in this structure, each carbon must form 4 bonds. So that's 1, 2, 3, 4. 1, 2, 3, 4. So those are now hydrogens. Those are now hydrogens. So that is the structure I've shown over there. It has 2 carbons and 1, 2, 3, 4, 5, 6 hydrogens. So that is the second of the alkanes. You could have yet another one, the third one. And how did I come? Now this is what I've done, the carbon, carbon, carbon. Now this one board 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And those are hydrogens, hydrogen, 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 and hydrogen. That is the third. So structural formula, molecular formula of the third of the alkanes. Now this formula can also be summarized into what we call a structural formula or a skeletal formula. A skeletal formula. Now a skeletal formula, in a skeletal formula, I just start with a carbon, and I don't have to draw across. Then that's another carbon, and then when I turn, it becomes another carbon. So 1, 2, 3. So that would be like that. So if I want to draw a compound that has say 5 carbon atoms, I start with 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. So that's a compound that has that's the skeletal formula of the compound that has 5 carbon atoms. That's a compound that has 5 carbon atoms. Now let's look at this structure and then try to come up with the general formula of the alkanes. Now a general formula shall belong to the whole of that homologous series. Now when you look at this structure, and so each carbon atom is bonded to two hydrogens. Each carbon atom is bonded to 2 hydrogens. Now let's even look at this. Each carbon atom is bonded to 2 hydrogen, then you have the 2 hydrogens at the end of the structure. So what is the general formula of the alkanes? If an alkane has n carbon atoms, then how many hydrogen will it have? It will have 2n, because each of these carbon must be bonded to 2 hydrogen. Then we add these 2 hydrogens at the end. So this becomes the general formula of the alkanes. So the general formula of the alkanes is CnH2n plus 2. Now you can see how I got to that. I just noted that each carbon atom is bonded to 2. So if I have n of them, I must have 2n carbon atoms. Then I have to add the 2 hydrogens at the end of the structure. So the molecular formula of an alkane with 8 carbon atoms shall be C8H 8 times 2 plus 2. That is C8H16. So that is the general formula. So where n refers to the number of carbon atoms. Now how do you name the alkanes? Now generally for the naming of organic substances, there's only one thing that you remember, that the name of any organic substance will consist of 2 parts. It will have a prefix. That's what comes first, I hope. Now the prefix stands for the number of carbon atoms. So we have any compound that has 1 carbon atom will have a prefix med. If it has 2 carbon atoms, it will have a prefix eth. If it has 3 carbon atoms, it will have a prefix prop, 4 but. The rest are as we have done in mathematics. We know a 5-sided figure is called a pentagon. So pent starts for 5, hex starts for 6, heptus, and so on and so forth. So that is any substance, whatever series it shall belong to. If it has 7 carbon atoms, it will have to start with hept. If it has 10 carbon atoms, it will have to start with dec. Now, the other part of the name of an organic substance is a suffix or the adding that starts for the series to which that particular compound belongs to. So if the compound is an alkane, it will always end with N. If it's an alkene, it will end with in. if it's an alkyne, it will end with ion. Alkanols will end with ol. Alkanoic acid will end with oic acid. For instance, an alkane with one carbon atom will be methane, because one meth, then it is an alkane, so it will have to end with N. An alkene with two carbon atoms will be eth, is standing for two. Then in is the heading for alkene. So we already talked about the various formula. Now we came across the empirical formula in form 3 that shows the simplest whole number ratio. For instance, ethane has the empirical formula C3. Ethane, we have said, is this compound that has two carbon atoms. It's an alkane. So CnH2n plus 2, that is C2H6. You simplify that, it will come to CH3. So that is the empirical formula of the alkanes. The general formula is generally for all the alkanes. Like the alkanes, you have CnH2n plus 2. Now we have another formula to call the empirical formula, the molecular formula. We've said that is like this one. Like this one, it has only summarized that has 2 and it has 6. So it shows the number of each element making the compound. Structural formula, we have said, will show the arrangement of the atoms in space. So it gives you it gives you more information than any of the other formula, and you can either summarize the structural formula into a skeletal formula or a condensed form of the structural formula. So we have an exercise here. We need to complete that table. Complete the table by drawing the structure of the first 10 alkanes. Like I can do the 10th one, and what is expected here. The molecular formula of the 10th one is C10H 10 times 2 plus 2, that is 22. I want to draw it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I put the hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So these are now hydrogens. These are hydrogen. So what is expected in the other one is the name. It is decane. The name is decane. It's decane. I need to remember to put the hydrogens. So, and I can draw the skeletal formula. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is that simple exercise. You can complete the table. You can complete the table. So write the molecular formula, the structural formula, the name of each of them, and then the skeletal formula of those compounds. So you note therefore that when you compare the alkane, the CH4 to C2H6 to C3H8, the difference between this and this is a CH2. The difference between that and that is also a CH2. We have added a CH2. Now, compounds that differ from each other by a CH2 are what we call a homologous series. So that becomes our definition from now henceforth. What is a homologous series? It is a group of compounds that differ from each other by a CH2. To obtain the previous from the present, you remove CH2. To obtain the next from the present, you add CH2. That is what we call a homologous series. Now, this homologous series will also have the following properties in common. They will have similar chemical properties, as we shall see as we study each one of them. The physical properties will show a gradual and steady change. That is it. They will have the same method of preparation. The general formula will be the same. That is what we call a homologous series, but that will be our definition of the same. Now we come up with another phenomena here. Now let's get back to the compounds that have 4 carbon atoms. And we have already drawn it like that. I hope we did that in the exercise. We have drawn it like that. But there is no reason why it has to be continuous. We have done that. We can take 3 carbon atoms, then we play around with the other carbon atom. If I press that carbon atom right there, that will be evil. Actually, that will be wrong. Yes, it will be illegal. It will be immoral. Why is that so? Because this board is too small. This board is too small. There is a lot of strain that has been introduced in that board. So what will happen is that this molecule will straighten up and it will look like that. So that is not a possible arrangement. Similarly, if I bring it to the end of the structure, again I have the same situation, and that will be completely wrong. That doesn't happen in chemistry. Now, but if I bring this carbon atom here to the second, then there's nowhere it can be. The board may be small, so the only thing it shall do is maybe become something like that. Become something like that, so that the carbons occupy the vertices of a tetrahedron. That's the maximum that can happen. That's the maximum that can happen in that particular case. So this is a correct structure. I can put the carbon on the second carbon atom, and then I put the hydrogen. Now, what will these compounds have in common? They will have the same number of carbon atoms, of course, and the same number of hydrogen atoms. You can convince yourself that this compound has 10 hydrogen atoms. So the molecular formula of this will be C4H10. The molecular formula of that will be C4H10. So the two have the same molecular formula, but their structural formulae are different. This is what we call isomers. So what are isomers? Isomers are compounds with the same molecular formula. Let's remove the word general. They have the same molecular formula but different structural formula. Now, isomerism therefore becomes the existence of compounds with the same molecular formula but different structural formula. Actually, these two compounds are therefore going to be very different. The fact that they have different structural formula will give them, especially their physical properties, they are going to be very different. I have a real life example of some commercial stuff. A long time ago, we used to have petrol that was called super. Now, some other petrol that was called regular. Super consisted of branched alkanes. It consists of branched alkanes in a process that is called cracking, then reforming. So in the refinery, the crude oil is separated into the component by refining. Then the refined fractions can be converted to more useful form by a process that is called reforming. So during reforming, in super, some of the straight-chain alkanes were converted to branched alkanes. Now the branching reduced what we call knocking. The branching reduces knocking. The mini explosions that you get in vehicles, that is due to ignition before vaporization. So this substance now, but the regular consists of straight chains. So in order to reduce branching in order to reduce the knocking in regular, you had to add an additive. You must have come across this. That is a tetraethyl. That was one of the uses of sodium that we gave in Form 2 to make an anti-knock agent, tetraethyl. So you add anti-knock to the regular, the one that contains straight chains, but the one that is branched is not. It will not knock. It has been made in such a way that knocking is not going to take place. So what are we saying therefore? That the two molecules, just because of the branching, they are going to be, even in terms of cost, they are going to be different. In usefulness, they are going to be different. Therefore, these are two different compounds. they have the same molecular formula, but they have different structural formula. That
is the story of lead-free petrol. Petrol for cars is mostly octane, C8H18. In the 1920s, when petrol started to be used for cars, the petrol-air mix in the cylinders used to explode too quickly before the spark, causing the engine to knock or jolt. If an isomer of octane was used, the petrol burnt more smoothly. Look carefully, there are 8 carbon atoms, so it is a structural isomer of octane. But what is its formal name? Pause and count the atoms in the longest chain. Whichever way you count, the longest chain is 5 carbon atoms long, so the name will be pentane. And off the third atom in the chain, there is an ethyl group and also a methyl group, so its name will be, pause and think, 3,3-methyl-ethyl pentane. But this compound is not normally found in crude oil and is very expensive. In 1923, scientists discovered a compound of lead with almost the same structure and did the job perfectly, lead tetraethyl or tetraethyl lead. You might remember that lead is in group 4 of the periodic table along with carbon. The lead addition helped the petrol to burn smoothly, but the lead atoms combine with oxygen, forming lead oxide. This comes out of the exhaust pipe as a fine dust and is very toxic. It has taken us until this 21st century to get rid of all the lead in petrol globally. But for 80 years, lead from car exhausts has been carried around the world and is even found in the ice in Antarctica.
So how do you name, if there are different compounds, then we shall need to name them. How do you name isomers? Now there are a few rules or a procedure that is adopted in naming isomers. The first thing that you do to name an isomers is identify the longest continuous chain. Longest continuous in the sense, now when I draw, if I've done, I have not made that chain. I am just moving. Then I get there, I just turn. I have not introduced any discontinuity. So bending will not make it discontinuous. But then I bring another carbon right there. If I start from here, I get up to there. That is continuous. But if I want to get here, I have to stop and start afresh. So this is not part of the continuous chain. It is not. So this part is becomes a branch. So the longest continuous chain is considered to be the parent alkane. So for instance, the one that you drew up there, the longest continuous chain has 3 carbon atoms. Therefore, it is a propane. The longest continuous chain is a propane. Now, the second thing I need to do is identify the branch, and branches are actually alkynes. Alkynes. An alkyne is simply an alkane, CnH2n plus 2 minus 1 of the hydrogen. So it becomes CnH2n plus 1. Yeah, so when you remove a hydrogen from an alkane, you get an alkyl. So if it has only 1 carbon atom, like the one I have here, it becomes a methyl. If it has 2 carbon atoms, it is an ethyl, and so on and so forth. You can get to the decal and the pentals. So the branch is identified. So, okay, we then therefore determine the type of branch, the methyl, ethyl, or the propyl. Then we name it. Then the other thing that we shall need to do therefore is to get the location. Where is that alkyl group? How do you do that? By numbering the carbon atoms, and we are allowed to number from either side as long as you are starting from the end. Yeah, so 1, 2, 3, all 1, 2, 3. Then we have numbered. We need to locate the methyl group. So it can be on carbon number 2 if I number from this side, or it can be on carbon number 2 if I number from the other side. So it is just 2 methyl either way. So it is 2 methyl. Note that I have the hyphen to separate the letter from the number. Now, if I have more than one of the branches, then I need to use di, tri, tetra, all that to show the exact number of the branches that I have. For instance, the compound I have here, now let's try to name it. 1, 2, 3, 4, 5. So it is derived from pentane. It is derived from pentane, the compound that has 5 carbon atoms. Now by putting some branches, and there are 2 branches, 2 branches, each of which has 1 carbon atom. So I have methyl branches, and there are 2 of them, so it is dimethyl. But where are they? 1, 2, 3, 4, and 5. All 1, 2, 3, 4, and 5. So this one is either on carbon number 2 or carbon number 4. This is either on carbon number 4 or carbon number 2. So either way it is 2, 4 dimethyl. I want to note very carefully that you cannot number from both sides. Please, let's avoid that. Numbering from both sides. So if you number from this side, you stick to that side. You cannot rotate this one by using number 2, then you rotate this one using number 2. So because in that way you'll have numbered from both sides. You're supposed to number from either side and not from both sides. So this compound is 2, 2, 4. Note that if you have numbers, that's the second thing that you need to note. If you have numbers, you separate numbers using a comma. If you have letters, you separate the letters using a hyphen. Now let's do yet another example. I want to draw and name the isomers of C7H16. I will skip the straight one. I will start with the isomers with 6 carbon atoms. 1, 2, 3, 4, 5, 6. Because if they are isomers, the number of carbon atoms must be maintained. They must, all the compounds I'm going to draw must have 7 carbon atoms. That is the only way that the molecular formula will be maintained if they have 7 carbon atoms. So I have 1 more carbon in my pocket. I remove it, I put it there. Remember we said you cannot put it there because it is evil. We don't want to commit a crime. So when I put it there, and I need to put the hydrogens, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that will be the structure, and these are all hydrogens. Please ensure that you put them. So what is the name of these isomers? It has 1, 2, 3, 4, 5, 6. So it is a hexane. It is a hexane now obtained by a substrate group or a branch, and the branch is methyl. There's only 1 carbon atom, so it's a methyl, and it's only 1, so I don't need a di, tri, and all that. Then I need to show where it is. How do I show that? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, and 6. So this branch is either on carbon number 2 or carbon number 5. Which one do I choose? Right. So the rule is you use the lower possible number, and the lower possible number is to separate the 2 from M using a hyphen. You can still get another one with the 6 carbon atom. 1, 2, 3, 4, 5, 6. I can't put the carbon right there. So that will be 3 methyl hexane. 3 methyl hexane, because 1, 2, 3. 1, 2, 3, 4. So 3 is lower than 4. So if I draw yet another one, remove that and put it there, that ceases to be an isomer. Why? Because 1, 2, 3, 4, 1, 2, 3. So it's still 3 like the one I've just drawn. So I am through with the isomers that have 2 carbon, that have a methyl. I remove 2 and put in my pocket. 1, 2, 3, 4, 5. I have 2 carbon atoms now in my pocket. I cannot put any of them there for the obvious reason. I can put one there and the other one there, and then put the hydrogen. What will that be? 1, 2, 3, 4, 5, pentane, small p. Now, methyls, 2 of them, so dimethyl. And where are they? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 2 is lower than 4. So that is 2, 2. Note that it is repeated. When I have a die, I must have 2 numbers. If I have a die, I must have 2 numbers. So that is one of the possible substances. Note that this is wrongly drawn. If you don't put the hydrogen, that is completely wrong. Another structure with 5, I still have 2 more carbon atoms. I can put one there, the other one there. That will be 2, 3, dimethyl pentane. Now I can remove that and put it there. So what will that be? 2, 4. 1, 2, 3, 4. 2, 4. I can remove the 2 of them and put them there. So that will be an ethyl. That will be 3 ethyl. That will be 3 ethyl pentane. Now I could also put the 2 of them there to give me 3, 3. And you can try all other. So you can now remove 3, put them in your pockets and try to put them there. Because it's a bit fun, it's a bit of fun to get now the 4. Put one there, put the other one, and put the other one. That's the only structure. So what will that be? 1, 2, 3, 4. That is a butane. 1, 2, 3 methyls. So try methyl, and where are they? So it can be 2, 2, 3 or 2, 3, 3. Which one is lower? 2, 2, 3 or 2, 2 or 2, 3, 2, 3, 3. Of course, 2, 2, 3 is lower. When you add them up, they'll add up to something lower than 2, 2. Than 2, 3, 3. So it is 2, 2, 3 trimethyl butane. That's how you name isomers. You can get to C8 and try to get as many isomers and name them. Now the next thing that we need to look at is the rough preparation of the alkanes. Definitely in the industry the alkanes will be obtained from crude oil. But what about in the lab? In the lab, alkanes are produced by a process that we call decarboxylation. That's a removal of a carboxyl group from sodium alkanoid. Now, I've heard some people talk of alkuna. Okay, you could use that to remember the alkanoid. So this, as we shall see shortly, is what you call an alkanoid ion. That's what you call an alkanoid ion. So from that, if you react that with the sodium hydroxide, what will actually happen is that all these will combine. All this will as long as the sodium hydroxide is in solid state, all those will combine. Then this will combine with that. That will combine with that. So what do you have here? When you combine the sodium, so we have 2 sodiums. You have 2 sodiums. You have 1 carbon, and you have 1, 2, 3 carbon. You have 3 oxygen. So that gives you sodium carbonate. Now the other one is an RH. Now this is an alkane. Let's look at a real example. That is the alkuna. R was this. This is what this is the R stands for an alkyl group. The alkyl group that we've just seen, methyl, ethyl, propyl. So this is an alkyl group. So it's an alkuna also. Then plus sodium hydroxide, just said that all these will combine to form 2 sodium, 1, 2 sodium, 1 carbon, and 3 oxygen to form sodium carbonate in solid state. Then the other one, this hydrogen just gets here, so that becomes 2n plus 2. So you have and CnH2n plus 2 definitely becomes an alkane. So note that you want to prepare methane, you have to start with an alkuna that has 2 carbon atoms, because this carbon will have to be used. If you want to prepare methane, you have to start from an ethanoid. You start with sodium, eth for meth. If you want to prepare ethane, you have to start with a propanoid, because one of the carbon will have to be to go into making the sodium carbonate. Note again that the sodium hydroxide must be mixed with calcium oxide. Why? Because sodium hydroxide is itself derequiescent. And yet, if this is going to happen, this must be intact. If it dissolves, then you'll have sodium ion and hydroxide ion separately. There's no way you're going to trace them so that they can combine. So this must remain in solid state. That is why you are adding calcium oxide, because failure to do that, it will absorb and dissolve, then it will not be available for the formation of the sodium carbonate. So the other reason why you need to add a calcium oxide to sodium hydroxide is because sodium hydroxide is too reactive. It attacks grass. It reacts with grass. So you need to dilute it. So the mix of sodium hydroxide and calcium oxide is what we refer to as soda lime. So if you ask for the reagent for this reaction, it is not really sodium hydroxide. It is soda lime. But the active substance is the sodium hydroxide. So that is just an example. The sodium ethanoate, so plus sodium hydroxide, all these combine to form sodium carbonate. Then this one attaches itself here, so you get to methane. So your ALKANE is sodium ethanoate. So because you want meth, because you want meth. Now similarly, if you want to get to get ethane, you use sodium propanoate. Sodium propanoate is sodium hydroxide. All these will combine to form sodium carbonate, then you get to that. Now next on chart therefore becomes the physical properties of the alkanes. Now you will remember that the physical properties of a substance will depend on the bond, and the alkanes are covalent with a simple molecular structure. They are covalent with a simple molecular structure. The intermolecular force of attraction for the simple molecular structure can either be van der Waals or hydrogen. The alkanes have van der Waals. So number one, the alkanes don't dissolve in water. That is rather obvious. We've just discovered that alkanes can be obtained from crude oil. So one of the substances found in crude oil is petrol. Does petrol dissolve in water? No. If petrol contains alkanes and petrol does not dissolve in water, then alkanes don't dissolve in water. And that is simple. So alkanes are non-polar. They don't dissolve in water. We remember what we said in acid-base salt, and now a polar substance is the one that has partial charges. So alkanes do not have partial charges, so they will be non-polar. They therefore don't dissolve in water. But as expected, they dissolve in organic salt, because the rule is polar dissolves polar, non-polar dissolves non-polar. So organic solvent like tetrachloromethane is a non-polar solvent, so it will dissolve alkanes. Now you ask me, the plastic jerry cans that you use to carry kerosene is made from is a hydrocarbon. You shall discover it is made from polymerization. So it's a hydrocarbon. How comes then it does not dissolve in kerosene? And the reason for that is the solubility decreases with an increase in size. So as it becomes longer, it becomes less and less soluble. Now the other thing that we can mention about the alkanes is that their melting point and boiling point are size dependent. They depend on the size. Why? Because they have van der Waals between the molecule. And van der Waals are the surface phenomena. The greater the surface area exposed for van der Waals, the stronger the van der Waals. So the longer the molecule, the more the surface area exposed for van der Waals. Therefore, the greater the van der Waals, the higher the melting point shall be. So we could therefore say that the melting point and boiling point are actually more of size dependent than relative molecular mass. Because if I take a molecule that looks like this one has 4 carbon atoms. The relative molecular mass is going to be the same as this other one. But you'll discover that this one has a lower melting point, because the approach, the surface area Now this one is a shorter molecule. So when you branch, you shorten the molecule. You shorten that molecule. Again, this branch will prevent the approach. Another molecule coming from down here cannot come very close because of this carbon atom. So branching will have the effect of reducing melting point. But that is basically what I need to say about the physical properties of the alkanes. Because they are non-polar, they don't dissolve in water, but they will dissolve in organic solvent, but the solubility will decrease with an increase in size. Now similarly, their boiling point and melting point will depend on the size of the molecule. So we discover that the first four alkanes are gaseous at room temperature. The lab gas will have everything between methane and butane. They will all be gaseous. Then when you go from carbon number 6 to say carbon number 10, they'll be liquid. But then when you, from there, the carbon number 11, the decanes, they will have, they may be solids. They will be solids, but some of them are weird solids, like grease. Is it really a solid? You touch it and it's colloidal in nature. So, but it is a solid anyway. So from there, then you have things like bitumen, the tar that is used to fix roads. That is also a hydrocarbon. So the graduation in melting point and boiling point depending on the size of the molecules. The other thing that we need to concern ourselves therefore is the chemical properties of the alkanes. The first thing that you need to say is the alkanes obviously burn. Alkanes will obviously burn. I think we have first-hand experience on the same because we use the alkanes as fuels. The lab gas will be made from mostly butane. If you look at, there will be mostly butane. Biogas is actually methane. The kerosene and the petrol, they are all burning. But what are they burning to produce? They are burning to produce carbon dioxide and water. So they burn to produce carbon dioxide and water. So you oxidize that, you also oxidize that. You don't combine the whole of that with oxygen, as some people will want us to believe. It cannot combine the whole of that with oxygen. It is actually destructive. It will break down, so you will get carbon dioxide, you'll also get water. So we can write an equation here for the combustion of methane. Remember, combustion is not simply heating. That is important. Combustion is not simply heating. You don't just draw an arrow. Don't just draw an arrow and say carbon dioxide and water. That will be magical. That will be magical. How will you balance the oxygen? How will you balance where will you get the oxygen from to balance that? So combustion involves the addition of oxygen. So we add oxygen to that. We get carbon dioxide plus H2O. Remember, if you have limited supply of oxygen, you are going to get, you may get carbon dioxide. If you have limited supply of oxygen. So let's balance that equation. There are 2 carbon there, so I need to put a 2 there. There are 6 hydrogens there, so I need to put a 3 there. And now I need to balance the oxygen. These are 4 plus 3, 7. How do I make these ones 7? How do I make those ones 7? And I was taught that I can multiply by 2. As long as it's a molecule, then multiply out by 2. Don't leave it as a fraction. If you do that, it will be marked wrong. Apart from in thermochemistry, when you are allowed to use fractions, in all other, as long as you are told to balance equations, you need to leave it as a whole number. So multiply that by 2, multiply that by 2, multiply that by 2. And now we can confirm that the equation is balanced. 4 carbon, 12 hydrogen, 12 hydrogen, 14 oxygen, 8 plus 6 is 14. That is a balanced equation of that reaction. So balancing of equation is important, and the fact that you can get carbon dioxide if you have a limited supply of oxygen. Now the next thing that I need to mention is that this can either burn in a luminous frame or a non-luminous blue-green frame, depending on what? Depending on the size. Now we have seen tires burn. Huh? I hope we have. Look at the frame that is produced when you burn a tire. I don't know what you are doing with a burning tire. That is suspicious. Eh? So, but if you have seen a burning tire, you can bear me witness that the frame is very sooty and very yellow in color. So why? Because you are burning a very long chained substance. When you burn lab gas in air, it burns in a blue frame. As long as you have sufficient supply of air. But as the size increases, the frame becomes progressively more sooty. So the nature of the frame will depend on the size of the molecule. So that the short molecules will burn in a green, blue, non-luminous frame. The long molecules will burn in a sooty, yellow, luminous frame. The other thing about that is inflammability. Again, the short molecules are more inflammable. They will catch fire more easily. So that nobody knows that better than the victims of the Sachaguan tragedy, where they tried to fetch petrol and somehow it ignited, and it can easily ignite, even sparks from a nylon trouser. As you walk there and your trouser is producing sparks, and that is enough to ignite that. And furthermore, even if you fetched it yesterday, you will see that frame will follow you through, because as you travel along the path, it's volatilizing, you are leaving vapor. So if it ignites tomorrow and you fetched yesterday, itafuata tu penye ulitokea. It will just follow you and it finds you in the bedroom. So avoid siphoning petrol. Okay, you can siphon diesel. I never said that. A substitution reaction is the next. Now, what is a substitution reaction? This is a reaction in which hydrogen atoms is replaced by a hydrogen. That is in the presence of ultraviolet light. When you react a halogen, methane, let me put it this way. And you react that with chlorine. I'll put the chlorine like that. So what happens is, in the presence of sunlight, the chlorine will be broken down to atoms. It will be broken down to one atom and another atom. So what we call free radicals. Now this one is a very reactive species. When it collides with the methane, it will remove that hydrogen so that it can be stable. So it will form hydrogen chloride. So whatever other chlorine remains will combine with that. So what will you get? Something that looks like this. Plus hydrogen. Remember that reaction requires sunlight, because the first thing that you must do is break the chlorine to chlorine bond. So to form a free radical or an atom that can easily remove a hydrogen, so that now the other chlorine combines there. So note that there are two products here. Substitution reaction gives you two products. So you cannot just add. You have to remove something, and then just like in a match, in a football match, if you start with 11 people in the field and somebody gets tired, or your most dependable player comes along, what do? Remove one and then add another one. So that is a substitute. You say left, and the ref, you know that you are substituting. So somebody gets in and then another gets out. And that is what is happening here. A hydrogen gets out and is replaced. It's replaced by a halogen. And that will take place with all halogens. And the process can continue. So these are chloromethane. We call this chloromethane. You can still replace another hydrogen, as we have just said. So depending on the exact number of chlorine, the ratio, you have 1 to 1, you'll only replace one one hydrogen. If you have 1 to 2, you will be able to replace 2 of the hydrogen, and you get 2 hydrogen chloride, and you'll get dichloromethane, and you can get this is what we call chloroform. Those in biology knows that chloroform is used as an anesthetic. If you want to be humane as you dissect animals, we used to use trichloromethane or chloroform. So that is a structure. Now, tetrachloromethane is a solvent. We have mentioned it so many times. It's a very important solvent. We use it every other day. Now, finally,
this experiment models the industrial catalytic cracking of long-chain alkanes and shows that some of the products have shorter chains than the starting material and that some are alkenes. They have carbon-carbon double bonds. The experiment is carried out in a boiling tube, and you need to start by putting some mineral wool, not cotton wool, into the bottom of the tube. The initial source of alkanes is liquid paraffin, which has about 20 carbons in its chain length. Use a dropping pipette to add liquid paraffin so that it soaks into the mineral wool. You'll need about 2 centimetre cubed. Help that to soak in a bit. And just invert it to check if there's any excess. Put some catalyst into the tube, and we're using pumice stone. But you can also use pieces of broken plant pot. Both of these are silica based, and they mimic the silica and alumina-based catalysts that are used in industry. Now you want to have ready prepared a bowl of water with about 6 test tubes also filled with water and some bungs. Next you need an assistant who could possibly be a competent student, although actually I often do this experiment with 2 students and don't get too involved myself at all. And what you're going to do is to heat using a roaring Bunsen flame, and the hottest part of the flame, which is just beyond the blue cone, and you're going to heat the pumice stone. As you do so, some gas will escape, and your assistant needs to collect the gas in a test tube. You want to get the pumice stone good and hot before you go any further. Once you've been heating for about 10 seconds, then you can flick across and just briefly heat your paraffin soaked in the mineral wool. Then go back and keep the catalyst hot. The whole time, keep the catalyst hot and then just flick across to start the paraffin evaporating. You want to heat the pumice stone for about 10 seconds for every second that you're heating your paraffin. It is important to keep the boiling tube and its contents hot. If it is allowed to cool, water may be sucked back into the boiling tube and it can cause the boiling tube to crack. It's vital to watch the delivery tube for signs of suckback. If this seems to be starting, the solution is to continue to heat the boiling tube with the hottest part of the flame just beyond the blue cone and to remove the whole thing from the water. It is tempting to push the Bunsen closer to the boiling tube or to remove the heat, both of which will increase suckback. And you can see there are some water drops coming up the tube, and if I just keep heating those, then they should come out. Continue until 6 test tubes of gas have been collected. Okay, when you come to the end, and you need to remove it from the water and stop heating. It's really important that you remove from the water first and carry on heating for a moment. When you're happy that there's no water in the tube, you can stop heating, but I wouldn't turn off the Bunsen burner until you're convinced that everything has stopped. Then you need to test the gases. The first two you can discard because they will just be air from your boiling tube. Okay, the third one you can pass around the class and they can have a gentle smell, and it should smell something like camping gas, which is a mixture of propane and butane. The fourth one you can attempt to ignite to prove that you have made a flammable gas. To the fifth tube, you can add a few drops of bromine water, which is just bromine dissolved in water. And shake it up, and you can see that the bromine goes colourless. This shows the presence of an alkene, or a carbon-carbon double bond. Similar reaction you can do with acidified potassium permanganate. A few drops into the test tube. Again, shake it up, and you can see that that's changed colour, and it will go either to brown or a colourless solution, and again that shows the presence of an alkene or a carbon-to-carbon double bond.
Finally, the uses of alkanes are definitely, if you cannot remember any use of any alkane, just say it's used as a fuel. We don't have any alkane that cannot be used as a fuel. In fact, all of them are. All of them are used as fuels. Yeah, they will be the components of the fuels that you use. Petrol will contain these numbers, and lab gas will contain these. So they are all used as fuels. And now the alkanes will also be used to produce all hydrogen that is used, for instance, in the manufacture of hydrogen. Of course, the other source of that hydrogen is electrolysis, but we are not talking about electrolysis now. So if you crack alkanes, and when you crack, you break down a wrong alkane, CH6, maybe 14, it can break down. You'll be told what it produces. So if it breaks to CH3, C3H8, what will be the next thing? The next thing will be C3H. Now I need to balance. I have the six carbon are accounted for. Hydrogens have only 8. I remain with 6 so that they can be 14. I guess something like that. But sometimes you also get hydrogen. So you'll also be told. So cracking can also produce hydrogen. So I need maybe to put this as another 6. And it can crack to produce hydrogen. Cracking can either be catalytic or thermal. You can use a catalyst or you can heat under pressure. Now carbon will also produce a carbon black, the stuff that is used in toners. And now, of course, the manufacture of methanol, tetrachromethane, chromethane, and tetrachromethane, we have already talked about them, and those are very important compounds. And that proceeds to the alkenes. So what are alkenes? Alkenes are